I'm going to put these solutions up on OneNote too, all right? So you'll have them, everybody. Now, if you have questions about the exam, do me a favor. See me like in about a half hour after class. I got something to take care of right after. If you need to see me about something, and I'll do my best to answer your questions. But let me go through the exam, then I'll get the average for you. How's that? All right? So, and I know there's a lot of high grades. There's some high grades, let me put it that way. I don't know the percentage, but I've seen several where they did something stupid. But let me go through the first one. This is for test A. I had x of t is 1 over t, u of t minus 1 times u of t minus 3. So 1 over t basically looks like something like this coming down. And it only exists from 1 to 3 seconds. That's the function. That's the one you don't flip. It's just a shifted function like we talked about. The next one is u of t minus 1 minus u of t minus 3. That looks like this. You just draw it out there. And this is the one I think I put on the board, by the way, the day before the test. So I'm going to flip this one. So when you flip it, it goes like this. And then you move it through. You realize there won't be anything until 2 seconds transpire because there's no overlap. And once there's overlap, you're just doing an integral of this function where the overlap exists. It's not hard to do. An integral of 1 over t is the natural log. You evaluate the lower and upper limits. There's really just 3 regimes. From 2 to 4, it's natural log of t minus 1. And then from 4 to 6, it's natural log of 3 minus the natural log of t minus 3, and 0 else. That's it in a nutshell. And what he did look for when he was grading is sort of a logical order of things. When you had the windowing and stuff like this come through, that's what he was looking for. This is a harder problem than the one in the other test, so you're given a lot more slack with the grading. You got a lot. The second problem on test B was this one. And it was simply a function where you had x of t times, or minus x of t minus 3, this. And then you had t squared times u of t minus 3, which is this, or t squared. So here I'm going to flip this one and shift it. And when I do, I wish I had a small little rectangle. But basically when I flip that, I'm coming here. It starts at 0. As I shift, I'm integrating through. I'm integrating t squared dt, or tau squared d tau. And that is going to be tau cubed over 3. Evaluate at the lower limit, which is 0, versus the upper limit, which is t. So that'll give you this right here. Then after that, once the window moves through, the leading edge is out after 3 seconds. And then you have to worry about the trailing edge. And there it's going to be from t minus 3 to 3 would be the integral. And that's going to give you this right here. Now, you could have had it in several different forms, but he checked. And if there is a mistake, come see me. And it's 0 else. Those were the things. They both look like, when you draw those, they both have the shark. One looks like this. This is a forged leading shark fin. The other is like this, reverse. But they are basically that. And he was very lenient on the drawings. All right.
What was the graph for test 1B?
That's it. Okay. All right. Let's go to test 1B. Part 2. All right, this is the Fourier series analysis. In this one, actually, this is a problem that is, only thing I did is change the scale on the vertical axis. It's a homework problem. And we worked this very one on the board, actually. So you're going to take 2 derivatives. First derivative, you get a square wave. And the square wave's height is just the slope. If you go from 0 to 5 with a height of 10, the slope would be 2 there. From 10 to 0 with a scale of 5 seconds, over 5 seconds, that's minus 2. Then you take a derivative of that, and you basically get this. And it's a repeated series, so there'll be 1 here, and you can repeat it as long as you want. Now, after that point, then you're going to have something to show him. You're going to get a Cn double prime, which is 1 over t. By the way, I didn't say this, but t in this case is 10 seconds. That's the period. Omega naught is 2 pi over t, or it's simply pi over 5. And he looked for these, by the way. Those were worth a point apiece. He had to make sure he saw those. Then, after you get this, C double prime is 1 over t. The integral, really, it's over any period. He chose minus 1 to 9. It's got to be over a length of 10. And that way, he captures this one and this one, only 2 of them. And in doing so, you end up getting this, and omega naught is that. And then this is a version of C of n. It can be this or any form that looks like that, and you got full credit for any form. Now he did, the way you always check this is you see what you get for C1. Because if C1's right, it's likely that C of n's right. If C1's wrong, you know C of n's wrong. That's the basic way you do this. So then for C of 1, it's just going to be you plug in 1 for n, and you get this equation, right here. So it's minus 2/5 times this, and it's divided by pi squared. Or really it's this, but pi over 5 squared with a j is minus pi squared over 25, so the 25 comes up. You cancel 5 into 25 is 5. 5 times 2 is 10. Minus pi squared, and this, e to the minus j pi is minus 1 times minus is 1. So I have 1 plus 1 is 2. You end up with getting minus 20 over pi squared, or some form like that. And again, he wasn't real picky. He just checked the answers looking at C of 1. All right, now in test A, I gotta get some new glasses. Test A, give me one second. This is a very similar problem. The only thing is this one is the phase shift. I shifted it by simply 5 seconds. A delay or advance of 5 seconds, it doesn't matter. In this case, take the first derivative, you get this. Second derivative, now you get this. Now you have two derivatives, you have delta functions. After you have these delta functions, you need to get C of n prime, or double prime, pardon me. And that's 1 over the period's 10, omega naught's pi over 5, same as the other one. And do the integration here, and when you do this, let's just sample the value of e to the minus j omega naught nt at the point where the delta functions turn on, which is 0 and 5, and he does that there. And then you end up getting this. And finally, your answer looks like this for C of n. You'll notice it's the same as the prior one, except without the minus sign. And your final answer is going to be 20 over pi squared when you evaluate it with n equal 1. Very straightforward. Matter of fact, this was a problem that it literally was right verbatim out of the homework, with the exception of the scale. It's just I had a scale, I think 5 in the homework. I have 10 here. All right, now, problem 3 was the simple, this is going to be Fourier transform problem. And I saw a lot of people, well, at least it appeared to me that people used Laplace transforms understanding, and they just substituted in j omega for t, since these things were valid only for t greater than 0. That's perfectly legit. You got full credit for it if you did it right. All right, or you could use the formal Fourier transform methods, and there's just minor differences. But for this one, everybody I think knows e to the minus 6t u of t goes to 1 over 6 plus j. So then you could use modulation theory, since this is cosine of omega naught t. Omega naught is 4, so you get 1/2 times 1 over 6 plus j omega plus 4 plus 1 over 6 plus j minus 4. And again, you're just taking this and shifting it and locating it plus and minus 4 and putting a 1/2 in front and adding them. Y'all follow me on this class? Do you remember doing modulation? On this one, the second part was duality. This is the one people had trouble with. Now, on this one, I kind of went over the top to trying to make sure you got this one right. On the day before the test, I put this problem up there. I don't know if you realized it, but it was this problem in a nutshell, with different magnitudes, with a different phase shift, but essentially this problem. So first I said delta t goes to 1, delta of t minus 2 goes to e to the minus 2, e to the minus j2 omega. This is the shift property. In other words, anytime you get a time delay in time, it's going to be a phase delay here. Next, p tau of t, the pulse goes to tau sync of omega tau over 2. Tau sync of tau over 2, going this way. He doesn't do it though. And this way, goes to 2 pi times p tau of technically minus omega, but because it's even, it's just plus omega. So that's the pulse there. And then finally, you go ahead and do you have 2 pi scaling, and there's a factor of 2 here because the magnitude is 2 here. So now you have this, and you know that this sync goes to this right here, and that's the same exact function we have. And then the phase, e to the minus j2 omega, simply means it's delayed by 2 seconds. Based on a fundamental property, you could just say x of t minus any tau here shifts over as e to the minus j omega tau times x of omega. That's the property. Follow me on this, class? Yes, sir.
So would it be like h omega be...
Pardon me? Say that again.
In that case, it would be like 2e minus j2 omega times like the pulse...
Times this, 2 times p tau of tau here is the actual width, which is 4, isn't it?
Yeah.
All right, and then you put that omega in there. That's it.
Okay.
Yes, sir.
So how do we turn this e to the negative j omega t into a pulse function?
no, not that, this is the property. Any function x of t minus tau transforms as e to the minus j omega tau times x of omega, all right? The x of omega is the pulse function. This is just simple phase delay. Time shift, a delay in time is a phase shift in frequency. That's the property. Now, a lot of people I think got confused, and I'm not sure why, but I tried to make sure I put that on the board the class period before I asked it so everybody would understand what I was looking for. It wasn't meant to be tricky. You're going to get tested on duality again. You better make sure you're good with this, because on the final exam you may get 2 problems that require duality. It's used several times. It's a very powerful property. You just have to spend time thinking about it. It's not that difficult to master, but you can't just look at it once. You have to spend time. It's like convolution. You have to do a lot of them to get good. All right, next problem over here. This was the one, instead of a cosine, a sine, imagine that. So I have sine of 10t to the minus 2t u of t. Well, first I do this, e to the minus 2t u of t goes to 1 over 2 plus j omega. I know the sine function will render a j over 2 times the actual x of omega shifted to plus 10, where the actual omega naught is, and to minus 10, only as a subtraction sign. That's one way to do it. Now, some people, what they actually did is chose to just use the Laplace transform of this, and they remembered this form, omega naught over s plus a squared plus omega naught squared, and simply made sj omega, and that's perfectly acceptable. If you did it right, you got full credit for that. So either of those solutions is acceptable. And it really didn't matter to me. Here, this is the same as the other function for the, I wanted the inverse, the h of t. Same as the other function with one caveat, the scale is 3 here. That's the difference. Do you follow me on that, class? That's the only difference. So again, and you might as well just say that for this one, you had to know this. He looked for something like that, then this. And then after that, he went ahead and divided by 2 pi. Tau in this case is, if you take a look at this, tau in this case is going to be 6 right there. And he puts it down, and then he has a scale of 3. And when all is said and done, go from there, and with the time delay it becomes this. It is very straightforward to do this, class. I'm just repeating what I did last time. There's nothing about this that's in any way troubling. We literally did this problem on the board. I don't know if you realize that. Literally that problem. All right? Now, the next problem was the circuits problem, and this is the one, by the way, this kind of stuff, expect on a final exam at least 2 circuits problems, all right? At least 2. Remember that. And you'll probably get another circuits problem in the next test too. And the reason I'm saying this is that what you learned in circuit analysis with Dr. Irwin or whoever you had is something that is going to keep repeating itself coming at you in every course just about. You must master circuits. And there are people that haven't, and that's troubling. You must understand circuits and the way to solve them. You'll never get away from this, especially in your upper level courses. That's assumed, and they assume you know Fourier transforms and Z transforms. Well, at least Fourier transforms very well, and Laplace transforms. And I cannot underscore how important it is for you to do that. If you have a weak area, something you need to spend time on, do it now. Get it under your belt, because it's going to keep on coming up. I had to do a review of some of this stuff in radar the other day, and I can see that a lot of students I taught that I knew were good students, they had no problems. It was a breeze. They were bored. But I saw other people that I didn't teach, and they're struggling and concerned, and they're puzzled by all sorts of things. And that scares me, because now they're going to fall further and further behind. They can't even master the material I'm showing them until they have the basic toolbox filled. So remember what I'm telling you. This class is extremely important for a lot of your other classes. Next, with circuits. Circuits in this course and digital are probably the underpinnings of electrical engineering. If you do well in all of those and get it under your belt, you're going to do well probably in electrical engineering, electrical and computer engineering. But if you have weaknesses, they're really going to be brought out in your upper level courses. So getting back to this thing, this is a basic circuit. Now this is a circuit where you have 5 U of t, and this is, what is this, test A or B? B. This is a typical circuits problem that you will be asked to solve most likely by somebody at some time to show that you're an electrical engineer. Something like this. I'm telling you the truth. My wife worked at Intel. She told me that's what we were at. They give you these things to make sure on paper, if it says you're a 4.0, you actually know what you're doing. It's not scan sheets all the time that you're guessing well. And that's one of those things. They give you these type of things that interrogate you. And if you don't know, then they're probably not going to hire you. So I'm leveling with you. You can talk to your friends. I'm not lying. They have to make sure you are what you say. And this kind of a circuits problem is trivial. And as a matter of fact, I think my wife she didn't have this one. She had one similar to this, but it cracked me up when she told me. So I better be careful here. I'm not sure if I should have said that on Intel. All right, scratch it. It wasn't Intel. It's a joke. Back to this thing. If I have 5 U of t, now I'm going to put this thing in the Laplace domain. There was no energy stored. By the way, I generally don't give problems where you have residual energy in the circuit at t less than, or for t of 0. And the only reason I don't is because that's covered in other courses. That's covered in your circuits courses. Remember when you did the flipping of switches for transients? There's always a voltage or a current at t equals 0. So you've seen enough of that. I get down to this, and I'm going to say this has an impedance of simply 1 over Cs, and since C is 1/2, it's 2 over S. This impedance is just S because L is 1, and this is 3. So now I get a transfer function, and by doing so I take this impedance, 2 over S, divided by the series impedance. Does everybody say it's a series circuit, and what I'm doing is voltage division, right? Give me a show of hands here to make sure. This one worries me. All right, so then I get this transfer function, which is really V out of S divided by V in of S, right? Now, once I have that, I can manipulate this all I want, or I can just take this transfer function and multiply it by the input voltage to get the output, which is 5 over S. So when I do that, then I multiply downstairs by S, I get S squared plus 3S plus 2 over 2 over S right here. And then I go ahead and factor this, and S squared plus 3S plus 2 factors as S plus 1, S plus 2. And now I have this, and now I have to do a partial fraction expansion, right, class? As we've done many times, we've done probably at least 10 of these in some way, shape, or form on the board, as far as I could count. When you do this, you get the values of A equals 5, B equals minus 10, C equals 5, and then you do the inverse. I chose the easiest ones. I didn't want to give you one with e to the minus AT cosine and something like that where you can foul that up when you're fatigued and tense. These are very simple ones. This goes to 5 U of t, A over S, right? This one's a simple pole. It goes to the scale factor of minus 10. It's decaying at minus e to the minus t U of t, and this is simply 5 over e to the minus 2t. Again, this is a problem. I don't know if you recognize it, but this very circuit's out of the homework. And we did that. We did not have the scale of 5, to be frank about it. And I think I even put an exponential there, which makes it a bit harder. You had another simple pole. And for the last problem, number 4, here we had U of t, and we had this. So if you looked at this, it was a template. The only difference is the values of R, L, and C. In a sense, only really a couple values. So here I have U of t. I have 1/4. This is 1. So this is 4. This is S. This is 4 over S here. And this is simply 1 over S. My transfer function is the output impedance right here over the sum of these impedances, S plus 4 over S. And then I multiply it by the input, which is 4 over S. Excuse me, is 1 over S. And in doing so, I'm going to get S squared plus 4 over S squared plus 4S plus 4 right here times 1 over S here, and then this is a perfect square. That's S plus 2 squared, and I get this. Agreed, class? Going down, you're going to have a simple pole A over S, then B over S plus 2, then C over S plus 2 squared. And at this point, it didn't matter how you figured it out. To get A, you simply cover up the S and evaluate this at S equals 0. To get C, you multiply through by S plus 2 squared and evaluate at S equals minus 2 to get that, which is going to be minus 2. And to get this one, you could do the derivative method, or you could just match coefficients to get B. It didn't matter to me which way you chose to do it. Anyway, these will be the values, and then going back into the time domain, the 1 over S goes as U of t. Since A is 1, it's just U of t. B over S plus 2 will be B, which is minus 1 e to the minus 2t. And this is going to be minus 2t e to the minus 2t. And both of these really should have a U of T on them, but that's the only thing. And again, the test itself was not meant to be something threatening or overbearing or anything like that. The only thing I tried to do is make sure I interrogated you the best way I could about the fundamentals. Convolution, Fourier transforms, Laplace transforms, and really, and then the inverse Laplace on this one too. And Fourier series analysis. All right, now, I got through that crank call. I know it's Friday, and after a test is given back, people don't want to hear a lot of new material. I want to do one thing today, just one. And we'll leave it there. What? When do we play next?
Saturday.
Who do we play? Kansas? Barkley was asking for Kansas. By the way, that game, my heart just can't take that. When you're up by 9 points, and it looks like a sure win. I had a meeting right after that. A bunch of professors come in, they're sweating. Glad it wasn't me. All righty. Tell you what, let me get you the average. I think I owe you that. And then I'll get to what I wanted to do today. Oops, no, I'll leave that on. Let me see what it is, because I don't know. What time do we play?
8:30.
What?
I'm pretty sure it's 8:30.
8:30 or 1:30? 1:30? Tomorrow. They play Saturday.
No, what time? That's what
Oh, there are some 40s. I take it back. There are some perfects. All right, the test average was 76% percentage-wise. So I'll take a look and see what I can do. I got to make sure there's no zeros added into there, that somebody didn't take it. So I'll let you know if there's any scale. Or I can't say for sure yet. Anyway, now let me do one thing. And there were 40s. Somehow, handing them back, I didn't see it. But there's several people that made perfects, I guess. And I know there's some 39s. I saw myself in 37, so that's good grades. This is the thing I want to tell you about. Yeah, I want you to listen. Now, what we've done so far is we took convolution in the time domain, and we didn't really talk that much about the discrete domain convolution. Does everybody recognize that? We are going to talk about discrete time convolution more. And it'll be related to something called the Z-transform that we talked about just briefly. Didn't we just touch on it? All right, now we've covered Laplace transforms, both synthesis and analysis. Remember how you can synthesize things if you use negative feedback with operational amplifiers. Do you all remember that class? You will be asked to do something with synthesis at some point. It may be on the final, but remember this, it's not over yet. All right, so keep that in mind. I'll do my best to bring you up to speed on that. In every aspect of it. We have done Fourier series analysis. That is for something that's periodic and repeats itself forever. For instance, a power line signal, something like that. We've done that, and we've done our best to try to analyze signals in the simplest way. And my opinion is the derivative method beats the heck out of integration by parts over and over again. So I'm just telling you, I try to give you what I think is the easiest way to do it. You will see this it'll blend right into the DTFT series analysis and Z-transform analysis. That's why I talked so much, spent some time on that. We use Fourier series analysis to get the input-output relationships for any periodic waveform into a filter by knowing h of omega and evaluating h of omega at n omega naught. Do you all remember that? And we found we got a single-sided cosine series to get the output in the time domain. This is important. And that a cosine of omega naught or n omega naught t plus a phase angle is really a phasor voltage. That's the key thing. It's a magnitude at the magnitude of whatever it is, and angle is the angle inside the cosine argument, and then you suppressed omega naught t or n omega naught t whenever you did phasor analysis. This is important to take in mind. Then after that, we did the DTFT. Does everybody recall that? The DTFT is basically the Fourier transform, only there's one major difference. Now we're sampling the signal, and because of that, we repeat the DTFT signature waveform over and over again, every 2 pi. This is important. So now we have something by sampling, it causes the entire axis to be populated with information that just repeats. But all the information you need really is between minus pi and pi in the omega domain. This is important, capital omega domain. Then we took that and we said, if we were bringing this into some real-time processing, we took the DTFT, a sampled waveform. We're getting closer to what we really do in the real world. And then we took that and we said, we're not going to have an infinite number of samples. We're going to have n samples. So that meant that the actual DTFT would now be presented to us at specific points. The points being 2 pi over n times k, or 2 pi over n times k, and divided by ts, where ts would be the sampling interval. And that would be the frequency that corresponds to the Fourier series, or Fourier transform frequency. Do you all remember sort of this, right? And that was so important because we could compare a waveform, a sampled waveform of finite duration, to the real Fourier transform of that signature if it was allowed to progress forever. Now, where we're going next, remember that the DTFT or FFT, do you all remember the DFT, right? That is something that can be done by a computer in real time. And the information gathered from that is so important because now you can take literally a real frequency shift that occurs in like a Doppler frequency shift by getting a bunch of information from just one pulse or series of pulses from radar, and then figuring out how fast the object is coming to you or away from you. I'm saying this because I do radar, so this is a real thing for me. And what you're doing is getting the tools to do this kind of stuff later on. And Wi-Fi, all the people that are involved with Wi-Fi and designing Wi-Fi architecture and things like this, this will also be beneficial to you. Now, the next thing we're going to do, if you think about this, we use the Fourier transform to create the DTFT to create the DFT. Do you all follow me? We used the Fourier transform, sampled the signal, got the DTFT, then had a finite number of samples, and we got the DFT, which will become becomes an efficient thing called the FFT. Now what we're going to do is we're going to do the Z transform. And I think I did this. I started with the Laplace transform, and I did a sampled signal. Do you all recall this? How many do? Didn't I say what the Laplace transform was in here and sampled it, didn't I?
The last thing we did was just the DFT. So.
All right, well, that's where I'm going. Now, listen to me before, I don't want to jump right into this. Let me just set the stage here. If you follow my rationale, before we did Fourier transform, that's a signal x of t, it's continuous time, it could exist forever, right? We eventually ended up with a DFT that's a much reduced form of that, but it's realistic to expect you can do that in real time with a computer. And you can present the data from that. And by adjusting that by that 1 minus e to the minus j omega t, where omega naught's adjusted by the 2 pi over n times k divided by ts, and divide that by j omega with that omega, then you can get a direct comparison to the Fourier transform that would be if that signal was allowed to go on forever. You just have to sample fast enough. So here's what I'm going to do. I'm going to start with the Laplace transform, which you know pretty well, right? Remember, this is analysis, not synthesis. And I'm going to go ahead and take the Laplace transform and take a sampled signal. And then I'm gonna get something akin to the DTFT, which will be called a Z-transform. Only it will not be in the J omega sample domain, it'll be in really the S domain, which is a real and complex value to it. Follow me on this? And then we'll see this is the real tool that we use, like we do the Laplace transform for both, and for really synthesis. The analysis you can do with the DTFT, but synthesizing things you need the Z-transform. So that's where I'm going. I'm not gonna hold you here on a Friday for 10 extra minutes, because right now you probably had a test. How many had 2 tests this week? What was the other one? EMAT. Dr. Riggs or Dr. Wentworth? That's not our test. Riggs comes up with tests right out of the pit. If you ever get a chance to take a look at some of his old tests, you're gonna, it's like, he asked that, really? All right, now, I'm gonna ask you, I'm not gonna give you homework this weekend, so catch up on your other stuff, but from Monday, the next 2 weeks is gonna be kind of intense. All right, and at the end, you guys remind me, not this coming week, the following week, at some point, let's vote on when our next test is. I want to get this next test date set in stone for a couple reasons. All right, so make sure the next 2 weeks you're here, because it's going to get pretty intense.